And now we are going to jump into our new material. So our goal for today is going to be to use series to solve differential equations. That's the goal. So we're going to start today looking at differential equations of the form y double prime plus px y prime plus qx y equal to 0. So today we are going to switch to the independent variable of x versus the independent variable of t. That's mostly because your book did it, and I'm not sure why, but I knew I was going to make too many mistakes if I tried to switch all the x's to t. I'm sure it's just like the first person who did this thing did with x's, so now everybody does it with x's. That seems to be what happens in math a lot. But from the way we've written this, it is clear that our independent variable is x, so it's all good. So we are going to define x naught is an ordinary point if p of x naught and q of x naught exist. So, right, we have this differential equation, and then instead of having constants in front of y prime and y, we have functions with respect to x. X is an ordinary, x naught is an ordinary point if it exists at both those functions. And then we call x naught is a singular point if p of x naught or q of x naught do not exist. So what we are going to be focusing on is finding series solutions near ordinary points. So that example that we just did was not a differential equation, but we were able to find the Taylor polynomial near an ordinary point because the function existed at that point, right? So we're kind of just extending this idea of when our functions exist, can we find series solutions? So we are going to just learn by example today. So let's say we have the function y double prime plus x squared y prime plus xy equal to 0. And let's say that x naught is 0. So that's the point we want to find our solution at. Is this point ordinary? Yes, it's good. In fact, does this differential equation have any singular points? No, right? Because we got x squared and x. So this differential equation has no singular points. So at the beginning of the semester, we did a little bit of like, let's just assume our solution looks kind of like this and figure it out from there, right? We're going to do the same thing here. So we are going to assume we have a solution of y equals the sum from n equals 0 to infinity of a sub n x to the n. Why do we like this? Polynomials are infinitely differentiable. So we like a polynomial, right? They're just easy to work with, easy to take integrals and derivatives of. We like polynomials. So we're just going to write, hey, this is the most basic polynomial I can think of. Let's use that. Or the most general, I should say, not basic. And then we are going to find y prime and y double prime. So can someone tell me what y prime is here? Yeah, so it's the sum, but what do we need to do with our index when we take a derivative? Add 1, great. So the sum n equals 1 to infinity of a sub n x to the n minus 1. And then y double prime is going to be the sum from n equals 2 to infinity, a sub n minus 1, x to the n minus 2. Okay. We have y, we have y prime, we have y double prime, we have a differential equation. We're just going to substitute those into our differential equation. So I'm going to have the sum from n equals 2 to infinity of a n minus 1 x to the n minus 2 plus x squared times the sum from n equals 1 to infinity a sub n x to the n minus 1 plus x times the sum from n equals 0 to infinity a sub n x to the n, and all of that equals 0. Our goal for these is going to be to see if we can come up with patterns for finding an. So we could write our final, like, hey, this is why, using just a power series. But in order to do that, I need to try and get to a point where I can combine all these things into one summation. Okay? So the first thing I'm going to do is I'm going to go ahead and distribute in my x squared and my x to the appropriate summations, just to like see, I know what indices we're at, but see what powers of x I've got. So I've got the sum from n equals 2 to infinity of a n minus 1 x to the n minus 2 plus the sum n equals 1 to infinity of the a n x to the n plus 1 plus the sum n equals 0 to infinity of a sub n x to the n plus 1 equal to 0. Okay. Are we okay with that? So I just distributed my x's inside my summation, which increased the middle one, the x increased by 2, and then the last one, the x increased by 1, the power. So what I'm noticing here is 2 of these summations have a power of x to the n plus 1. I want to get all my summations to have the same power. So we need to try and get that first summation to have an x to the n plus 1 as a power. So that means I need to increase the power of x by 3. How can I do that? Was a moth attacking you? Yeah. So if I need to increase my power by 3, I need to shift my index down by how many? 3. So I'm going to shift my index down by 3. So n equals -1 to infinity. And then all the n's can increase by 3 inside my summation. So I've got a n plus 3, n plus 3, n plus 2, x to the n plus 1, plus the sum n equals 1 to infinity, and those other ones aren't changing yet. Okay. So now all my x's have the same exponent, but I can't just combine my summations yet because of what? Yeah, the indices. Any idea how we can handle that situation? Bless you. So let's take this first one. Well, first of all, what index do you think I need to be shooting for all of these? Let's start there.
Equal 0.
You could try n equals 0. The problem is if you did n equals 0, that middle one would you'd have to change the power on the x. What you want to shoot for is your highest index. So we're going to shoot for n equals 1, okay? So let's just write out the first couple terms of my first summation until I get to n equals 1. So if n is -1, I get a sub 2 times 2 times 1 x to the 0. So that's my -1 term. Plus, and then my 0 term, I get a3 times 3 times 2 x to the 1. So that was my -1 term and my 0 term. So I just wrote out those first two terms. And now that I've written out the first two terms, my next thing would be 1, right? So now I can just say, hey, I've already written out those first two terms. So I'm just going to write n equals 1 to infinity, a n plus 3, n plus 3, n plus 2, x to the n plus 1. And I haven't lost anything because I just wrote out those first two terms separately and then was like, and then everything else. But I've sectioned off those first two terms, the -1 term and the 0 term. Does that make sense to everybody? Okay. I think I'm going to go ahead and write, well, the next one's not changing, so I can squeeze it in here. So my middle term, that one was already good. That started at 1. So leave it as is. And then my last term, if I want that to start at 1, how many, or my last summation, if I want that to start at 1, how many terms do I need to write out? 1. This moth does not want to leave us alone or whatever it is. So I just need that first term, because once I write that first term, then n will be 1, so we're good. So let's see, I've got a0 x to the first plus the sum from n equals 1 to infinity, a sub n x to the n plus 1, and then all of this still equals 0. The reason I do this is I need all those x's inside my summation to be the same so that like I've accounted for my constant term, like my entire constant term is pulled out and my entire linear term was pulled out. And then we're actually starting in the summation at x squared term. So let's try and group some things together. So my constant term is going to be 2a2 because my only term with an x to the 0 was that first thing right here. And x to the 0 is just 1. So good. Now let's look at the linear terms. So I've got this term and this term that are linear. So that's going to be 6a3 plus a0 all times x. So I grouped those linear terms together and then factored out the x. Plus the sum from n equals 1 to infinity of, and now I'm just going to group or combine all my summations. And also while I'm combining, go ahead and factor the x in plus 1 out. So I've got a, n plus 3, n plus 3, n plus 2, plus a n n plus a n, all times x to the n plus 1 equal to 0. All right, definitely a lot of work, but the overarching goal here was to be able to say, can I solve for my terms, right? So I have the constant term, the linear term, and then the general n plus 1 term. So if my constant term is 2a2, and this entire thing has to equal 0, what does 2a2 have to equal? 0, right? My constant term is 0, thus 2a2 has to also equal 0. So a2 is equal to 0. Now let's look at my linear term. I don't have an x to the first on the right. So what's the constant, or what does my linear term have to equal as well then? 0, right? Because I have a 0x to the one on the right. I just don't write it. So I've got 6a3 plus a0 has to equal 0, which gives me that a3 is negative a0 over 6. But that's as specific as I can get because I don't know what a0 is. All right. And then for all my other terms, I know that a n plus 3 times n plus 3 times n plus 2 plus a n times n plus a n has to equal 0. If you solve this for a n plus 3, you are going to get that negative a n times n plus 1 over n plus 3 times n plus 2. Okay. Do you notice anything about my a3 and my general a n plus 3? These are actually the same. If you were to substitute 0 for n into this formula, you would get a3 equals negative a0 times 1 over 3 times 2, which is 6. So what we can conclude is that a0 is arbitrary. We can't figure it out. A1 is also going to be arbitrary, right? We didn't have a formula for that. A2 is 0, and then we are able to start our recursion at 3, right? So a n plus 3 is going to equal negative a n times n plus 1 over n plus 3 times n plus 2. Okay. So if I was to write out a couple iterations of this one, because now I know my a's and I know my y all the way at the top was a n times x to the n, right? So now that I have these formulas for a n, if I was to write a couple iterations, I would get a0 plus a1x plus A2 times x squared, but what was A2? 0, so I'm just not going to write it. Minus 1/6 x cubed minus 1/6 x to the 4th plus 1/45. Oh, sorry, I forgot I forgot my A0 and A1, so it should have been minus 1/6 A0 x cubed minus 1/6 A1 x cubed plus 1/45 A0 x to the 6th. And then it kind of just continues. So this one, a pattern is not super obvious. What we're going to try to figure out on Wednesday is if there's a pattern to this. Okay. Any questions? Yeah.
Where did you get the 1/6? Like from?
Let's see. So that's the third term. So A3 equals negative A sub n. So that would be negative A0. And then 0 plus 1 is 1 over 2 times 3. So just using this equation. So if I wanted to calculate A3, what's my n actually?
And 1 and 4 and 1.
Yeah.
So on.
Yep. All right, let's call it a day.